Welcome. It's time for the next session. Please put your headphones on. Thank you for joining. In the next 45 minutes, we'll take you on a journey to modify an architecture so it can withstand the spiky peaks of the latest Super Bowl event. My name is Dennis Kieselos. I'm one of the solutions architects here at AWS, working with customers to achieve exactly that. In case you want to talk to us, there's also a Ask an Architect stand in the big exhibition hall where you can get in touch with us. It's right at the end next to the containers. So today, I'm glad to have Seb with me on stage. He's from Edjo. Please, Seb, tell us a bit more about your company and what you're doing.
Thank you very much, Dennis. And also thank you very much for you coming here and giving us the opportunity to present us what we have done, our efforts to prepare for this event. And also thank you for the AWS Summit for allowing us to present these results here. So first of all, about me. Hi, my name is Sebastian. I am Director of Technology at Edjo. That means I am also a tech lead of then multiple teams. And all of these teams have contributed to all of these efforts. But who are we? So Edjo is an edtech platform. We are live in about 150 countries. And on a normal day, our backend scales to about 250 EC2 instances and serves on a daily basis about 5 billion requests per day. But this is spread out over the course of an entire day. Now, everything that I'm going to tell you later on is in the context of playtime. And what is playtime actually? So playtime is an ad format. So it's about ads. And I hope everybody loves ads as a necessary evil, I believe. And what's it all about? On the one side, you have the advertisers. They would like to acquire users. And on the other hand, you have monetizers. They would like to make money by showing ads in their games. And for the users, there's not just the displaying of the ads, there's a little twist, they can get rewards. Now, looking at this and also at the product, you can already see some of the technicalities. So the product consists of something like images, you have some button that will also trigger a request, and you also have there other sections. So you can imagine when we talk about a load increase, it is not just a single API, it is multiple APIs that need to be served. So, but enough of that. Let's talk a little bit about the infrastructure and the backend itself. So, when the end users on the left-hand side are interacting with our product, they are using something written in Kotlin, Java, or in Swift, if it is in iOS, and they are also interfacing with something that is written in JavaScript or TypeScript. Now, once they hit the backend, they either hit CloudFront, that is mainly what we use for static content, such as images, or JavaScript, or sometimes even textual content that is static. However, if we have some dynamic content, for example, a user clicks or creates an impression, or wants to see what are my installed games that I already have, then all of this goes through our load balancer, through the ALB, and hits the backend that is hosted in ECS. Now in this graph, I'm only showing you one icon for ECS, but what you need to understand is there are multiple different ECS services running. In the backend that we're talking about, it's around 60 microservices that are running in parallel. And they are also communicating with each other. And for that, we're using SNS and SQS, such that we have a synchronous communication between the different ECS services. For end user data, we are relying heavily on DynamoDB because it is very reliable and allows us to store a lot of end user data. And we also work with Redis OSS, and that is mainly for ephemeral data storage. So some data that might expire over some time or is not for permanent use. On top of that, you can also see we use Kafka and also Druid. This is mainly in order to collect event data that we have from the application and store it in Druid for statistical analysis that we also use. Now, let's talk a little bit about the event. We had the opportunity to work with one of our publishers who was running an ad during the Super Bowl. And that means we will be getting a lot of traffic in a very short amount of time. And usually when we ran promotions, we could rely on auto-scaling. But I will get to that, what could be the complications of this particular event later. But Dennis will proceed with how autoscaling actually works.
Yeah, so in general, you saw we need a lot of capacity, right? So here, what you see is on the y-axis, you see the infrastructure costs, and you see the time on the x-axis. And typical, when we do a planning like Agile, they are planning for growth, for example, it goes up to the right? Because we are growing, we need more capacity. And in the traditional sense, if we look at we buy servers on our own, we are not using the cloud, it would be like a step function curve. We buy hardware, and at some point we notice, okay, to meet the demand, we need new hardware, so we stock up. The actual demand, though, is like a curvy line. And in case of Agile, it's even a line that has a spike at one point, and then it decreases again when the event is over, right? And our cost savings, when we look at these cloud economics and business cases that we calculate for customers, we have opportunity costs here because we have over-provisioning. We have more capacity than we need, and this is where AWS and the cloud comes in, right? What we also have is we may have lost opportunities because we have not enough capacity to even serve our users. And this may lead to a bad customer experience in the end, and we also want to avoid that. So when we are on AWS, we try to have a curve that has some buffer, but mostly matches the actual demand. So what we need to do in this case is we need to figure out what's the right capacity, what is the right number of instances that we need to provide. So we have both curves, we avoid under-provisioning, but we also avoid over-provisioning. And the question is now, how do we do it? How do we figure out what capacity is needed? And Seb will share a bit of the process on how they got there.
Thanks. So what you usually have is a wheel of actions that you do. So at first you need a script or a means to conduct load tests. Then from these you can conduct measurements using metrics like CloudWatch, or in some cases also Grafana, and also some profiling that you can do in your application in order to figure out whether everything is working. Now, I can already spoil, in most of the cases it will not be working, so you need to do some analysis, improvements, and deploy, and then fine-tune these improvements that you did. And this cycle needs to be repeated over and over. Now, for the load tests that we were running, we were asked to prepare for a load of around 100,000 users per second. So that's not just 100,000 requests per second. Every user can make up to 20 requests. So it could be a lot more requests that are hitting the backend, but it should be 100,000 users per second. And at peak times, it should even sustain 125,000 users per second. I mentioned already, we are using tools like CloudWatch or other metric tools in order to spot issues. So why do we need this observability? So for using these tools, we can learn about issues that we have in our applications. Standard issues are like, I have a lot of 503s in my backend API, or I have a lot of 400s and so on, that are pointing you to issues that you have. But in addition to that, the metrics that you have in the platform also allow you to drill down into the actual issue and also understand the customer experience. So you can figure out, even though you do not have so many error responses from your backend, your latency decreased massively, and this is why the user experience deteriorated. You can also then, of course, create your own dashboards and also your graphs in order to make it visible how well the services that you provide are actually operating. And also you can determine some of the bottlenecks that you might have. So you might be spotting, okay, a certain DynamoDB table is throttling, and this might be just the problem that I have in my application. Now, this is on the one hand the metrics and observability that I talked about. But one other thing that is also very important and necessary is actually some kind of profiling. So here I have an example that we also spotted during a load test. What you see here is focused in on a TLS handshake. And this might be a little bit confusing. So let me give you a little bit of context. So this is a TLS handshake that happens between the backend and the DynamoDB API. And what we spotted, for example, during the load test is that we have a lot of these happening, and these are actually unnecessary because the backend should just do it once and not do it over and over again. But the profiling in this case helped us to spot this issue and figure out that we were wasting a lot of resources on this thing. And now let's look at the actual load test. And what you can see here is a load test that is successful. So here for iOS, for the iOS APIs, we are reaching around 60K users per second. And the API is also really fast, so it responds within 30 to 50 milliseconds of response time. And the error rate is in the single digit range. So everything is looking fine and everything works fine. In order to run this load test, we used the tool that is called K6. In the slide and also in the QR code, you can find a link to the GitHub page of this project. And in the beginning, we of course used a single instance and everything worked fine up to a certain point of request load that we could hit. And the problem that we came across was that the single node or the single instance had a finite amount of network traffic that it can sustain, and we were just hitting this limit and were not able to scale to the 60K or 100K of users that we actually needed. And this is why we used the Kubernetes operator for K6. And there, what you do is you spool up multiple pods of K6 in a Kubernetes cluster, and then in parallel you can hit the backend with more and more requests. And now, what I mentioned already earlier, maybe as a reminder, what we always did is we do a load test, then we do improvements, and then we repeat. And there are many, many of these cycles that we actually have to do. Now, I showed you much earlier how a successful load test looks like. But the most common case is actually a failing load test. And I would like to walk you through a little bit what we found there. So this is one example. You can see we are nowhere near the request load that we actually want to hit. And also the response time is already hitting a ceiling. So we are at multiple seconds. So the API is not actually responding well. So let's walk through a little bit of the architecture and how we could improve that.
Yeah, and what we do is we start with a data layer, and Azure uses, as we heard in the beginning, uses DynamoDB. And for DynamoDB, you need to understand there are different modes of operation that we offer, right? And those who are already using DynamoDB, it's a serverless database. So you need to decide between one of the operation modes. And on the left-hand side, you see the provision mode. The provision mode is basically for static workloads, so you can predict what you are up to. You have gradual ramps. You basically configure the capacity from the beginning. And the pricing is based on the read and write capacity that you provision. On the right-hand side, you see the on-demand modes. It's for unpredictable workloads, and there may be also times where a workload is idle. And it's like well suited for events like this where you can't really predict the traffic. So you can just set the on-demand mode, and we will take care of the rest. And the pricing is then based on the count of read and write requests. So while we think that on-demand mode is a great configuration for this use case, what's the actual issue when you were using on-demand mode?
Yeah. Actually, so what we thought in the beginning, okay, on demand is actually a great idea because it's a single on event. We just make all tables on demand. Maybe it costs a little more, but we do not have the hassle to think about all of the scaling. But when we tried that in the load test, we discovered that even on-demand tables have some kind of limitations in the background. And what you need to keep in mind and what you need to consider is that even an on-demand table needs to be pre-warmed. That means if you hit a cold on-demand table now with a lot of traffic that comes into it, it will not scale automatically. It will scale over time, of course, in the background, but it will not scale fast enough. And you need to tell it in advance how much scale it actually needs.
Yeah, and for that we have a setting that you can put into your table setting. So you can basically pre-warm the DynamoDB table in advance. You can just set it, and even when it's already created and you are running a production workload on it, you can also configure it. It's a non-blocking operation, so you can continue using the DynamoDB table while this operation is carried out. So you see here, it's a simple configuration where you can just increase the warm throughput, and then DynamoDB will take care of the rest. But obviously, you need to pay attention to it and configure it accordingly.
Now, of course, actually, so I would like to mention, in the end, some of the tables we actually made on demand, and then also edited a warm throughput. But we did not do it with all of the tables. Many we kept on the provision scale. But even if you have a provisioned capacity, and the capacity that you have is well above what you actually see in your metric as usage, you might still experience read throttles or write throttles. And this was, in the beginning, also a little bit puzzling for me, where that comes from. And the underlying reason is the following. So DynamoDB is, of course, is completely managed, but is also scaling automatically in the background. But when it scales horizontally. And what it does is it adds more and more partitions to the table. And this happens upon multiple triggers. I believe, if I'm not mistaken, it happens on the data, but it also happens on the write throughput that you have on your table. However, what you need to consider is the capacity or the read capacity you can have on one single partition of your table is still limited. Even if you scale the read capacity of your table to 10, 20,000, it will still not work, and you will still experience throttles. And what actually then we had to do is to figure out what kind of query is actually causing this, or what kind of thing is actually causing this. And for this, we used in the end the CloudWatch contributor insights for DynamoDB. And it can tell you which of the keys that are being queried are hot. That means which are queried most of the time. And this is here a sample graph of one of the tables that we had. Now, what we did in the end, or what was the problem in the end, we had a certain configuration that is specific for the publisher app that we're working with. But because this entire promotion happens in the same publisher app and all these millions of users are coming from the same app, we were hitting always the same key in the test. So what we had to do is, or what we actually did is we added a cache, an in-memory cache for this. And that had actually two effects. On the one hand, we, of course, reduced the amount of read capacities and the throttles, but also we reduced the amount of network traffic we have between the backend and the DynamoDB API. And in our application, both of the things need to be optimized because the application itself is also quite network heavy. But there are also alternatives that you might consider.
Yeah. So while Edjo was capable in modifying the application, right? So they had the developers working on the code base anyway. There may be things where you have like a different organizational setup, or you say like, at this point in time, we will not make changes to the application anymore. And for these use cases, we offer a managed cache solution, which is a DynamoDB accelerator, or in short, we call it DEX, which is a fully managed, available, highly available cache for DynamoDB that you can plug between your application and DynamoDB itself. So the API remains compatible, no changes to the application required, and you can achieve similar outcomes with DEX in this case. So now that we have sorted out the database part, let's look at other services that are involved in the architecture, and the next one is compute. And obviously, you think of us as a hyperscaler, as a customer, we will scale compute automatically, right? The cloud is unlimited, so obviously that shouldn't be an issue. Where do you need to pay attention to? It's called auto-scaling, because in auto-scaling we have different scaling policies. And you as a customer, you need to configure the appropriate auto-scaling to make sure the auto-scaling works the way you want it, and at the point in time where you need the capacity, it's scaled enough. So, and here you see the variety of scaling policies that we are offering. And on the left-hand side, we start with the reactive scaling policies, which is the simple or step scaling, which means you basically configure in what steps should we add capacity to it after a certain threshold is crossed. On the right-hand side, next to simple or step scaling, we have the thermostat style control, like a heating. You say like, I want 21 degrees, and the heating automatically calculates how much heat needs to be generated. So this is something you can also do. You set a target metric where you say, this is my metric, and then auto-scaling, please automatically add the instances as needed. This is obviously reactive. We have some proactive auto-scaling policies on the right-hand side, namely scheduled scaling. This is something where you can put in a date and you can say like, all employees come to work at 8, I need more capacity so the system can withstand all the issues we have. Or we could, in theory, also do something for the Super Bowl saying like, there is this event in time and I want to be ready and scale it at that point in time. And then the last one is, because this is still manual and a bit static, right? The last one is predictive scaling, where we used some AI/ML features and looked at the history on how your application was behaving and how the requests were developing, and then predicting the usage pattern based on the history. Obviously, if you have one-time events like this, it's not really helpful. So the pain points of auto-scaling are, with spiky workloads, you always need to pay attention, because auto-scaling itself, although it auto-scales, it needs some time to scale up. And if you have a very spiky workload, like we have in this situation here, it's not fast enough to catch up with all the users that are coming. So you need to plan ahead and configure it accordingly.
Yes, and now let's talk a little, or give you a little bit of detail of how this actually worked. Because usually, when you run a promotion or an ad, you will get a peak, and then the users will not come all at the same time, but they will be spread out over a longer period of time. So this is also why in all of our previous promotions that we did, which run on push notes or other TV ads, the auto scaling that we did actually worked quite well, and we did not have to do some interventions. But in this particular case, the publisher opted for a different implementation or a different way how to conduct this. So what actually was shown in the Super Bowl ad was more like a QR code. The users scan this, and then all of these users are collected in some kind of live stream. And the whole purpose of this is conversion and retention, in order to keep the users engaged and have more and more users coming to the app in the end. But what happens then in the end is all of these users, millions of users, are collected, and then in the end, all of them are dropped simultaneously to us. That also means that this increase is happening far steeper than we would otherwise have expected. And also, yeah, this also means then in numbers, it's about 10,000 times traffic spike that happens in under a minute. And this is also why we cannot rely on auto-scaling in this particular case, and we need to have the predefined scale. Now, let's also zoom into other parts. So we tackled a little bit ECS scaling and DynamoDB. Let's talk also about the ALBs, or the load balancers. And what was new to me was also that ALBs have limits. In all of the years that we have worked with AWS, and our whole business has scaled by multiple factors, 10 or more, we never experienced any issues with load balancer limits. But as it turns out, load balancers have also some kind of limitations.
Yeah, And how do you deal with it? We heard it's by default we have capacity inside the load balancers that fit for most of the use cases. But what we need to do in this case is make a load balancer capacity unit reservation in advance. So that is something you can do. It allows you to prepare for these sharp increases where the auto scaling that the load balancer does is simply not fast enough. So you specify a minimum amount of ALB or NLB, depending what load balancer type you are using capacity. And this allows you to handle this traffic surge. And the load balancers will continue to auto-scale afterwards as you are used to. Then a second option that you can even combine is you could also use a sharding strategy, which is a form of horizontal scaling. By default, as Seb said, usually you don't need it, right? But by doing that, you can basically split the load between different load balancers, which means you split it off. You have Route 53, you have a DNS distribution, where the DNS routes it to multiple load balancers involved. And by doing that, you basically load balance between different load balancers. So that's an additional scenario that you consider. Should you be unsure if that's needed or you should make use of it at all, talk to us. That's what we at AWS are there for. So now we've been talking a lot about compute, load balancing, all these components that are inside the synchronous request chain. But what we noticed in the beginning, there are also asynchronous components inside the architecture. So let's take a look on what you have done there to optimize it.
Yes, thanks. So previously, in this graph, you see for asynchronous components, we use SNS and SQS, and also Kafka as a sink for the data that we put to Druid. Now I can already spoil for Kafka, we didn't have to do so much scaling. We already prepared the cluster such that it can withstand the load. But I would like to talk a little bit more what we did for SNS and SQS. So SNS we use mainly to fan out messages. So we have one SNS topic and we have multiple queues that subscribe to this topic. And then each of the ECS services that is interested in this topic consumes from this queue. But then let's talk about some of the limitations that came up during the load test. So SNS has service quotas. That means you can, I believe the default is 10K messages per second that you can send to SNS. And now in this test, we quickly ran into this limit, and then the SNS API started to throttle us or started to slow us down or reject the messages. And what we did in order to work around this is, on the one hand, we are batching the messages, because each SNS message can store multiple some 100 kilobytes. So we can put multiple messages into one. And on top of that, what we can also do is we can compress the whole thing. And then in the end, we save both on the number of messages being sent to SNS and also the data transfer that we have outside of the application. Again, the application is very data intensive, and this needs to be kept in mind as well. And with this trick, or with this method, we can use the capacity that we have more efficiently than we could use before. Of course, I understand there's some trade-off. If you start batching messages, you will have to wait until you send something out. But if you have so much traffic on the application, the delay is actually negligible. And yeah. So let's talk a little bit about service quotas.
Yeah, exactly. So you already mentioned it, right? And you may now think, okay, service quotas, does it make sense? What are they there for? Does AWS want to bother us by putting limits onto the service? No, we don't want to. So we have service quotas on all of our services, not just because they are sensible quotas that we put in by default. Doesn't mean that you can't raise them. There are some hard quotas where we say, like, the service teams designed the service in the way it works, and you may need to rethink on how the architecture is designed. And then there are others where we just put in something where we think, okay, you should consider raising it, and you can simply do it in your console and request more of the service to use. So we know, okay, you revisit it and you are sure you want to use that amount, right? So smaller increases are automatically approved. And when there are very large requests of quota increases, we may ask back, so the support engineer may reply to you and say like, look, what are you actually doing? What's the use case? Why do you need it? That's potentially not something that we see how customers use the service very often, because the more you use the service, the more costs occur, and there may be a better way of solving a problem, right? So this is the way it works. So just because you are hitting a limit somewhere doesn't mean you can't use it. You just need to look into what's the current setting, and then you can adjust it. That brings me also to the point how we collaborate as the AWS team. So besides me, as a solution architect working with Edjo, we have other AWS people here in Germany working with customers. Obviously, every customer has an account manager. And depending on the support level that you have signed up for, there's also different ways on how you can use enterprise support. And as part of enterprise support, you can get technical account manager, and most of the work actually in this regard was done by the technical account manager, who really looked into the architecture and discovered potential bottlenecks in advance. We revisited the different components together, and we can also pull in other specialists from our global team should our local knowledge not be sufficient, right? And ideally, if you come up with a similar scenario, the earlier you reach out to us to ask us for guidance, the better we can support you and set up some proactive sessions where we can then work backwards from the event date and set you up for success so that your event in the end goes well. There are some other things. We also do cost optimization as an example. There are workshops that we can run together. So something to look into. It's a self-service platform. You can just use AWS without talking to us, but sometimes it also makes sense to work together. So now that we've been looking through all the components and the architecture, I'm curious, how did it go in the end?
Thanks. Actually, so we had a very successful event. But first, let's talk about the final results of our load tests. So we tuned the backend or improved the backend so far that we could sustain the 100,000 users per second load over a period of 15 minutes. That is far longer than we actually have to do on the game day. The load that we had during the promotion was also less than half than what we prepared for. That also means we were somewhat over-provisioned, but we had a very good safety margin, and this is a far more preferable spot to be in than being under-provisioned. That also means the system stayed super stable despite the fact that we had a super increase in the traffic load. And I also would like to show you how it looked at the time. And keep in mind, this is about 4 a.m. in Hamburg, and everybody gathered inside the office. And this is how it looked like then on the game day. As you can see, everybody was super happy. And also on the graph, you can see how it looked like. So basically, you start with a horizontal line, and then you just have a vertical line going up. So let's talk a little bit or a few minutes about the lessons learned. So my key takeaway that I would like to tell you is that you should use measurements under load. And measurements are, on the one hand, of course, metrics and also the profiles that we talked about. And the reason for that is everything that we talked about what particular implementations that we did might be interesting to you, but might not just be relevant for the application that you are running. I think the tools that we presented to you today are far more interesting than the particular implementations that I showed you. And what you should find is that the backend language that you are using has some kind of tool that allows you to profile. I think almost all of the backend languages that you use have this. And you should also use metrics for CloudWatch, but also DynamoDB, also Grafana metrics that you have, in order to spot the bottlenecks and issues that you have in your scaling, in your architecture. And also as a closing note, I would like to thank again the AWS support team. Dennis already mentioned that you can submit support requests. And I can tell you also from our experience, this worked really well. So in this whole iteration of the improvements, there are many support tickets that we issued, both for service quota increases, but also for troubleshooting with issues. I think we had also several sessions about, okay, what will be the EC2 node pool size that we can have? How many nodes do we have available at the time of the day? And there the AWS support was really, really helpful. And I would like to thank you for that.
Yeah, it was really a pleasure collaborating, which brings us to the end of the session. Please just remember, visit us in the hall. We made big announcements today. You can in hall 1, you can visit us and learn more about that. If you have other questions to us, please come to the front after the session. We will also be around here later on. There's a happy hour where I'm happy to chat. And as said, you can also find my colleagues at the Ask an Architect booth in the hall next to the containers in the end. So with that, we'd like to say thanks to all of you for spending the lunch break with us. There's still food, so you didn't miss anything. If you like the session and you think we should provide more content like that, please make sure to rate us in the app and provide a 5-star rating. Thanks in advance and have fun for the rest of the day.